Welcome my dear students. New session. In the last class we discussed about some properties of inverse of a linear transformations and show that the homomorphism. In this class we discuss about the space of LUV. Means LUV space means simply we can say that we have a collection of all the linear transformations. We have all the linear transformation that form a vector space, and that vector space is called is a space of LUV spaces, or also is called as the home of UV. So let's start with this. We have to taking like this. We have suppose some T and S be any two vector space linear transformation from V to W. Then this means this LUV means we can say that is V such that we have a collection of all linear maps. We have to just say that T from Ti from V to W such that T is you have a linear. So we have to just say that collection of all the linear transformation. LUV spaces simply we can say that collection of all the linear transformation. And now we just try to show that this LUV spaces is also form a vector space. For LUV spaces forming the vector space, we need two binary operations. One is the sum of addition, and another is a scalar multiplication. So first we try to show that take a two how to define a sum of two linear transformation, and how we define a scalar multiplication of a linear transformation. So let's begin with the sum of two linear maps. So we have a T from U to V and S from U to V be a two linear transformations, and we have to consider a M. M is equal to, we have to just say that M is nothing but is equal to, we just say that M is nothing but is equal to, we can say that is a form of a S plus T, means sum of a two linear transformations S and T. We define M of U is nothing but is equal to S of U plus T of U for all U belongs to U. Now our objective is first we show that this MU is also is a linear. So if we show that this MU is also linear, they should satisfy both the condition of a linear map. One is a additivity and one other is a closed under scalar multiplications. So that means we just say that we have to try to show that this M satisfy both the condition. This M is closed under addition and also closed under scalar. So we prove that this M is a linear. So M is linear means we have to take any two elements of M of U plus V should be M of U plus M of V, and M of you have a alpha U should be alpha times M of U. So if we successful prove to these two condition hold by M defined in this form, then we can say that this M is also is a linear map. This is linear map is a sum of two linear maps. Okay, so we just try to solving this where alpha is some scalar. So let's begin with the take any two elements V. So this means we can take a U1 and U2. U1 and U2 are the element of a U. So we write M of U1 plus U2 can be written as a S of U1 plus U2 and T of U1 plus U2 by the definition of M, because M of U we have to define in the form of a S of U plus T of U. Now we have also given this S and T are U to V is a linear map. So by the linearity condition, because S is a linear and T is a linear, this can be written in the form of a S of U1 plus S of U2, and T is also linear. By the linearity of a T, we can say that this is equal to T of U1 and T of U2, and then we can say that clearly because by the definition of this S and T are linear, and this we can write in the form of a, again in the form of a take a sum of these two. So just we leave here, and then because S and T are the linear, we using this. Another way we have to calculate the M of U and T of U is separately. So we just take a M of m of u1. So you have a m of u1 is nothing but is equal to, you have a s of u1 plus t of u1, and m of u2 is the same as a s of u2 plus t of u2. Then we have a m of u1 plus m of u2 is nothing but is equal to, you have to just say that s of u1 plus t of u1 plus s of u2 plus t of u2, and this is the same, we can just say right into this form. So this means m of u1 plus u2 the same as the m of u1 plus m of u1 plus u2. So this means by the definition of m. Now we use the here associativity and commutativity, then we can use this condition. We have to use first is associativity, then we use the commutativity of a vector addition of a v, because this is s and t are from u to v, with this s of u1 is the element of a v, as t of u1 is also the element of a v, and v is a vector space. So we just say that by the vector space we can use the associativity condition and also use the commutativity conditions of in a vector space of a v. So this means you can say that this m of u1 plus u2 is the same. So the first condition is clearly hold. Now we try to show that the second condition. The second condition is m of alpha u1 is should be this. So we just take a m of alpha u1 can be written as a s of alpha u1 plus alpha u2, and again s and t are we have a given as a linear. So s and t are from, we have a from u to v is a linear map. So this means this can be written as alpha times s of u1 plus alpha times t of u1. And now because again this is a vector space, so this can be written as a alpha times of, we can just write as a s of u1 plus we have a t of u1, and then this is nothing but is equal to alpha times m of u1. So this means this satisfy this condition. So this is clearly we can say that. So this is we have a property of a multiplicative is this. So this means we can say that into this form. So this proves that M is a linear map. That means we take a two linear transformations. If S and T are the two linear transformation, and then M is nothing but is equal to sum of these two linear transformation is again is a linear transformation. So that means we prove that M is a linear. So this means this M is called the sum of S and T and denoted by S plus T, and this S plus T is nothing but is equal to, we have to denote it into this form. So we have to the sum of a two linear map is again is a linear map. So this is the one of the conditions we have to prove that. That means if you take a two linear maps, then sum is again is a linear map. Okay, now we have to just try to another is a product scalar multiple of a linear map. So S be a u to v be a linear map, and alpha be a given any scalar. U and v are the vector spaces over the same field of scalar, and alpha also belong to the same field. Now consider a p from u to v defined by p of u into this form. So now we have to try to show that this p defined to this form is again is a linear map. So again p of is a linear map, we can use the property. We have to p of u, you take a u1 u2 are the element of a u, and because alpha is already there, so we take another scalar is lambda be a scalar. Okay, so we just state p of u1 u2 can be written in the form of a this form by the definition of linear product of a p of u, because p of u can be written in the form of alpha times of a you have a s of u. So by this definition, now because s is you have a given this s is a linear, so this can be written as s of u1 plus s of u2, and now this is the element of a v2. This can be written as by the distributive property s u1 plus alpha times s of u2. So this means we can say that into this form. Again by the product of this this definition of a p, we can write this is nothing but is equal to p times of a u1 plus this is we can say that p times of a u2. So, p of u1 plus u2 can be written as a p of u1 plus u2. So, this means under additions we can just say that it satisfy the conditions for under additivity is there. Now, this is because of vector space. So, this is now we have to try to find the lambda times of this, because of lambda times is this can be written as alpha times S is a linear map. So, this can be lambda times you have a S of u1, and now again by the vector space alpha lambda, and then we can write as a S of u1, and this is nothing but is equal to, these are the element of a scalar, this can be written as lambda alpha times S of u1, and this can be lambda times S alpha times, this can be written as alpha times S of u1, and this is lambda times S of u1 is nothing but is equal to, you have a p of u1. So, ultimately we have to show that p of lambda times u1 is the same as lambda times p of u1. So, in this case we can show that this p satisfy this p defined by p of u is defined by alpha times you have a S of u, satisfy both the conditions of a linearity and addition and homogeneity, additivity and scalar multiplications. So, this means we can say that this p is also is a linear map. So, we can say that clearly this vector space conditions. So, this p is a we prove that this p is a linear map. P map P defined above is called is the scalar multiple of S by alpha and is denoted by alpha S. So, this means alpha S is defined into this form. This is scalar multiplication. This scalar multiple of a linear map is a linear. So, that means we can just say that you know that when we say that vector space, I say that under addition and we have a scalar multiplication satisfy the certain properties. So, first we need two operations are there, addition and scalar multiplication. Here we have to study about the linear space L of UV spaces. LUV spaces, I just say that is a collection of all the linear transformations. So, for this if we try to show that this later on we just try to show that this LUV space is a form a vector space under the addition is defined by this addition of a two linear map, and scalar multiplication is defined by this. Under these two binary operations, this LUV space is a form a vector space. So, later on we show that this proof of this also provided, but let with this sum and linear map of scalar multiplication, we just try to some exercises, try to some examples. So, first we try to take a two linear map V3 to V3, and T of x is defined into this form, S is defined into this form. Try to find what is S plus T. So, we have to S plus T, what is the sum of these two linear map. Now, you that we take any element, arbitrary element into the this V3. So, we just take a x1, x2, x3 are the element of a V3. Then we take a S of, you have a S plus T of, you have a x1, x2, x3. By the property we can just say that when you define M of u can be written as a S of u plus T of u. By this property, this can be written as S of x1, x2, x3 plus T of x1, x2, x3. And this can be written as a S of this and T of this. So, S of this is you have a 2 times x1 plus x2 plus x3, and then you have a minus ka x2, and then you have a 2x3, and then plus you have a T, you have a x1 minus x2, and then you have a x3. Now, by the property sum of these component wise, we can just say that this is nothing but is equal to, you have a 2x1 plus x2 plus x3 plus ka x1 minus ka x2, then you have a minus ka x2 plus ka x2, and then you have a twice x3 plus x3, and this should be is equal to x2 is cancel out. So, you have a 3 times of x1 plus x3 comma 0, and then you have a 3 times of x3. The sum of these two linear maps is nothing but is equal to we define into this form. So, okay. So, this is clearly into this form, and now scalar multiple of this alpha times of s is equal to this. So, this can be written as alpha times of s is you have a 2 x1 plus x2 plus x3 minus x2 comma twice x3, and this is nothing but is equal to 2 times of alpha x1 plus alpha x2 plus alpha x3 minus alpha x2 twice alpha x3. This is the scalar multiplication into this form. Now, I just try to what is the this s plus t. So, try to what is the dimension of this s plus t, because s plus t is also you have a v3 to v3. So, I just try to what is the kernel of this s plus t. So, if we have to kernel of s plus t means this is by the we try to find the kernel of s plus t. If we try find the kernel of s plus t means we have to just say that s plus t is equal to you have a we can just say that we say that s plus t of u is equal to 0. So, this means this quantity is equal to 0. So, you have a 3x1 plus x3 0 x3 is equal to 0 0 0. This implies that x1 is equal to 0, x3 is equal to 0, and x2 is anything. So, this means kernel of this s plus t is nothing but is equal to the form of a 0 x2 and 0 such that x2 is the element of a R. So, this means span of kernel of s plus t is the form of a you have a 0 1 0. So, this is the kernel of span of the kernel of this thing, and then we can say that dimension of kernel of a t is equal s plus we just say that dimension of kernel of s plus t is equal to you have a 1. Similarly, we can find the range also. So, range is also you have a second term is 0. So, x y this is range is you have a as proper subspace of this x and z plane. So, RT is nothing but is equal to RT is the form of a you have a x 0 and z such that x and z is the element of a R. So, this RT is nothing but is equal to you have a xz plane, and then we can say that this is nothing but is equal to we can say that if we find a dimension. So, dimension of a range of a t is you have a 2 and range of s plus t. So, this means dimension of a range of s plus t is equal to you have a 2 is there, because we can write this is the form of a 1 0 0 and we have a 0 0 1. These are the two element in the basis. So, clearly range of s plus t is also dimension of s plus t is equal to 2 and dimension of kernel of s plus t is equal to 2, but you know that the dimension by the rank nullity theorem we know that the dimension of a V3 is equal to 3 or R3 is the same as a 2 plus 1. So, this is said to verify dimension rank dimension theorem for s plus t also. So, we just say that s plus t is equal to this, and alpha for this also we can getting this rank is equal to 0 alpha 3 x3 0 x2 0, and then we have x1 is also 0. So, if we take a product of this, then the kernel of this product is a 0 subspace, and then the dimension of this is equal to 0, and this is clearly x y z is completely R3. So, this is 1 1 onto this transformation, we can just say that. Okay, so, this means we can just say that. Now, to take another example. In this example, we take a R3 to R3 and S is also R3 to R3 BT linear maps defined by E1 is equal to this E2 and E3. S of E1, E2, E3 we have to define in different way. Now, we try to find what is our S plus T. There is a two method. First, we can one of the method we can write this basis element as a linear combination of the elements of this, or we can directly calculate s plus t e1, s plus t e2 and so on like this. So, we just try to first we directly use the only definition. So, we just said s plus t e1 is equal to s plus e1 plus s t of e1. Now, s of e1 is equal to, you have a e3 and t of e1 is equal to e1 plus e2. So, this is e1 plus e2 plus e3. Then similarly, we can calculate s plus t, you have a e2 and then you have a e2 plus t of e2. Now, you have a e2 is equal to twice e2 minus e3, twice e2 minus e3 and plus e3 is equal to twice of e2, and now s plus t we have to calculate over e3, s of e3 plus t of e3. Now, s of e3 is equal to 0 and e2 minus e3. So, 0 plus e2 minus e3 is equal to e2 minus e3. So, we just say that this is we have to write into this form, and similarly we calculate what is a 2t v3. So, v3, so 2t e1 is equal to 2 times of a t of e1, and e1 is equal to e1 plus e2 is equal to this, and similarly we have to calculate 2 of e2, and 2 if e2 is equal to 2 times of a e3, and then similarly we have to calculate 2 times of a e3, 2 times e3, e2 minus e3, then 2 times of a e2 minus e3. So, this complete the we have to calculate into this form. Now, I just there is a problem. If we have a T and S and T are LUV spaces are injective, then T plus S need not be injective. Okay, so, we try to this is true or not. I take for example, we take S T from R2 to R2 and define we have to take a T of x y is equal to, you have a x and y, and this is clearly is a linear map, and then I take a S from R2 to R2, then we have to take a x and y is equal to minus x minus y, and this two map is clearly is a we have a linear map. We can easily verify that this clearly T is linear because T of x plus y is equal to this, and then now we have to try to what is the our s plus this is clearly linear, and now we have to check is this 1 1 or not. Now, what is the kernel of this? So, kernel of a T we calculate, this implies that T of we have to just say that x y is equal to 0 0 implies that x y is equal to 0 0 implies that x is equal to 0 and y is equal to 0. This implies that kernel of a T is nothing but is equal to is 0 subspace means T is 1 1. Now, similarly is kernel of S is equal to, we have to write this implies that find the kernel of S. This means S of is equal to 0. This implies that S of x y is equal to, you have a minus x minus y is equal to 0 0. Then we can say that this is equal to x is equal to 0 and y is equal to 0. It implies that kernel of S is also 0. This implies that T is 1 1. So, that means we have to take a two maps S and T. We both the maps are linear and also injective. Now, we check is this if in what about the sum of these two. So, I just take a sum S plus T over x plus y is the sorry x comma y. This is the same as a S of, by the definition of a sum of a two linear map is the form of a x and y, and S of x y we define as a x and y, plus we have to define as a minus x minus y, and this is clearly x plus minus y, y plus minus y, and this should be equal to 0 0. So, this means we can say that clearly S plus t xy is equal to 0 0. So if we take two different values and that is giving the same values, this means clearly s plus t is not a 1 1. So if we have to take if u and v are the two s plus t of a u is equal to 0 and we have a s plus t v also 0. This implies that if we take these two are the different images, then we can say that clearly there is two different values giving the same images. So this means clearly that u is different from v. So we have assuming this u is not equal to v, but we show that s plus t u is the same as a s plus t over v. So this clearly s plus t is not a 1 1. So that means we show that if s and t are to 1 1 map, but s plus t is need not be an injective. So this is the very important result. We can say that if we take a two injective maps, take a sum of these two injective maps clearly, but the sum of these two injective maps need not be an injective. So this complete the because this is not true. So by the is not true, we have to provide a counter example for this thing. Okay, so now next move is the one more problem. This is I just take another way. We take any r to rn to rn. We take a t is identity map and is equal to minus identity is equal to 0 map, which is not injective. Kernel of this kernel is nothing but is equal to whole r to the power n. In this case, you have a kernel of this s plus t is nothing but is equal to r to the power n. So this means sum of two injective linear maps need not be injective. Okay. So now we take some other problems. Suppose we have to take a t from defined into this form and s is defined into this form, and then he said that different linear transformation s plus t 3s minus 2t and alpha s in the terms of v1 v2 v3. Okay, so t for v1 v2 v3. So we take first we take a general formula for s. So we take some v1 v2 v3 is the element of a R3, and because these are the E1 E2 E3 are the standard basis, so this v1 v2 v3 can be written as the linear combination of this. So we just say that is equal to v1 E1 plus v2 E2 plus v3 E3. And now if we take s, so s of v1 v2 v3 can be written as a s of v1 E1 and v2 E2 v3 E3, because s is a linear. This can have v1 of we have a s of E1 plus v2 s of E2 v3 s of E3. So v1 so we have to just say that s of v1 v2 v3. So we have a s of E1 plus v2 s of E2 plus v3 s of E3. Then v1 s of E1 we can substitute where E2 minus E3. So we say E2 minus E3 plus v2 substitute the value for s of E2. S of E2 is equal to E1. So we just say that E1 plus v3 substitute the value for s of E1 plus E2 plus E3. So you have a E1 plus E2 plus E3. Now we have to just say that this can be written in the form of this. Clearly this is no E1 is here, so this is equal to v1. Sorry, this is v2 plus v3, and here you have a v1 and plus you have a v3, and this is equal to minus v1 plus v3. So s can be written in the form of in this form. So s of v1 v2 v3 in this form, and t of v1 v2 v3 in the form of this 2 v1 minus 3 v2 v1 minus 3 v2, and then is equal to 4 v1 plus 6 v2 and 4 v1 plus 6 v2, and then you have a v3. Now what we calculate? We calculate s plus t. So we have a s plus t of v1, v2, v3, and this is nothing but is equal to, by the definition of a sum of this, we can write as a v1, v2, v3 plus t of v1, v2, v3. As of v1, v2 we have to v2 plus v3, v1 plus v3 minus v1 plus v3 plus s is equal to, you have a 2v1 minus ka 3v2, and then you have a 4v1 plus 6v2 and v3. This can be written as sum of this. So this is equal to, you have a v2 plus v3 plus 2 times of a v1 minus 3 times of a v2, v1 plus v3 plus का 4 v1 plus 6 का v2, and then you have a minus v1 plus v3 plus v3, then is equal to, you have a 2 times of a v1, and then v2 you have a minus का 2 times of a v2, and then you have a plus का v3, and then you have a v1, and this you have a 5 times of a v1. I just say that this is equal to 5 times of a v1, and then you have a plus ka 6 of v2 and plus v3, and then you have a minus ka v1. So this is s plus t is nothing but is equal to, we have to write into a this form. So clearly here you just okay. So this is, we have to getting the sum of these two. And another problem is 3s minus 2t. So this means we multiplied by calculate here the 3s. 3s you have to multiply it by 3 here, then you have a 3 here, then you have a 3 here, and then we have to taking the another is minus 2. So you have to multiply it by t is a minus 2, and then take a sum in the similar fashions, and then we have to finally similar fashion we can calculate the alpha of s1 is equal to similar fashion we just take this. So we have a 3s minus 2t. So we can say that 3s minus 2t is similarly can be written as a, we have to write as a 3s of 3 of s. I just directly write the values of this like this. We take a 3s minus 2t over v1, v2, v3 can be written as a 3 times of a s of v1, v2, v3 plus minus 2 times of a t of v1, v2, v3, and this can be by the product rules. We can say that this is 3 times of a, you have s of v1, v2, v3, and plus minus 2 times of a t of v1, v2, v3, then 3 times of a s v1, v2, v3 is equal to, you have a like this, you have a this v2 plus v3. So we have a v2 plus v3, and then v1 plus v3. So we have a v1 plus v3, and we have a minus v1 plus v3, and plus minus 2 times of a t. T is equal to, you have a 2 v1 minus 3 v2. So 2 v1 minus 3 v2, and then you have a 4 v1 plus 6 v2, 4 v1 plus 6 v2, and then we have a v3. So this can be written in the form, or we can just say that we can write this can be written in the form of a 3 v1 plus 3 v2 minus ka 4 v1, and we have a, sorry, this is v2 not v3, this is v2, 3 v2 plus 3 v3, and minus ka 4 v1 and plus ka 6 v2, and then you have a 3 times of a v1 plus 3 times of a v3, and then we have a minus ka 8 times of a v1 or minus ka 12 times of a v2, and then we have a last one is equal to minus ka 3 times of a v1 plus 3 times of a V3 and then plus minus का 2 times of a V3. So this is sum of 3s minus 2 is this. We have to simplify this. This means we have to simply say that minus का 4 V1 and then you have a 9 का V2 plus 3 V3. Here you have a 3 V1 and this is equal to you have a minus का 5 V1, 3 V3 and minus का 12 V2 plus का 3 V3 minus 3 V1, 3 V2 and this is equal to minus का 3 V1 and plus का V3. So this is nothing but is equal to you have a 3s minus 2t V1, V2, V3 is equal to this value. So this complete the proof of this example. So now at this point I have to stop this class at this example. In the next class we discuss about to try to show that this LUV space is a form a LUV is form a vector space. Under the addition we define S plus T form and scalar multiplication we define alpha times of a S. These are the two, under these two binary operation collection of all linear transformation is form a vector space. We have to prove this in the next class. So thank you very much for this class.